Andhra Pradesh Public Service Commission, Government Polytechnic Lecture Examination, Electronics and Communication Engineering 2013 Previous Question Paper Part 2. 47th question. The closed loop gain of feedback amplifier is a gain obtained when the feedback loop is closed. Option 3 is a correct option. So in option 1 they have given feedback factor exceeds unity. Generally, the feedback network in an amplifier, closed loop amplifier, is made up of passive elements. Hence, feedback factor or feedback gain never exceeds unity. Next, amplifier gain with feedback is also referred to as closed loop gain because it is a gain obtained after the feedback is closed. After the feedback is closed. So correct option is 3. Next question. 48th question. The smallest of 4 H parameters in the transistor is either H. Correct option is option 1, that is output admittance, either in CE configuration or in common collector configuration or in common base configuration. Lowest value among all these 4 H parameters, lowest H parameter is output admittance H4. It is in micromos. So correct option is 1. So option 1 is correct. Smallest of all 4 H parameters is output admittance. Next question. If the Q point changes the H parameter of a transistor, so the Q point of the H parameter values depends on Q point. If Q point changes, H parameters obviously changes. Also, the H parameters of a transistor vary with temperature. So if temperature is varied, the H parameters of transistor gets changed. So the correct option is 2. If the Q point changes, then H parameter of the transistor also change. Next question. So various, so in the same question, some key points are, so different H parameters are H11 short circuit input impedance, H12 short circuit forward current gain, or HF. HR is open circuit reverse voltage gain, and HO is open circuit output admittance. Question 50. The voltage gain of common source. So this is common source junction field effect transistor depends upon its. So the voltage gain of common source. So this is a circuit diagram for voltage divider bias, common source configuration, junction field effect transistor. The voltage gain of this common source configuration with voltage divider bias, it is given by this formula. So minus gm capital rd by small rd plus capital rd plus rs plus gmrd rs, where rd is a drain resistance or output resistance, capital rd is a resistance collected to the drain terminal. So capital rd is resistance terminal to the drain terminal, small rd is drain resistance or output resistance, gm is transconductance of the junction field, JFET junction field effect transistor, and mu is amplification factor. So mu is a product of this amplification factor is a product of drain resistance into transconductance. Mu is equal to GMRD. So from this, the voltage gain of common source junction field junction field effect transistor amplifier depends upon its, one is transconductance. It depends on GM transconductance as well as external load resistance, that is RD, drain load resistance. So the correct option is 3, drain load resistance and transconductance. Next question. So in question 51, they have given two components, electric field component in x direction and electric field component in y direction, and we have to identify which kind of polarization it is. So let us see first the definition of polarization, different types of polarizations. Polarization is defined as orientation of electric field with respect to earth surface. Orientation of electric field with respect to earth surface. This polarization is of three types in broad sense. One is linear polarization, circular polarization, elliptical polarization. This linear polarization is of two types, either it is horizontal polarization and vertical polarization. In horizontal polarization, electric field is parallel to earth surface. In vertical polarization, electric field is perpendicular to the earth surface. Again, this circular polarization is of two types, left hand circular polarization, right hand circular polarization, based on the direction of rotation of electric field. And elliptical polarization is also of two types, that is left hand elliptical polarization, right hand elliptical polarization. Let us see the conditions for circular polarization. The necessary and sufficient condition for the wave to be circularly polarized is the field must have two orthogonal components, either in circular polarization or elliptical polarization. The, the field must have two orthogonal components and same magnitude whose phase difference is odd multiples of 90 degrees. In circular polarization, it has two orthogonal components with phase difference of 90 degrees. In elliptical polarization, it is also having two orthogonal components of different magnitude. Here, orthogonal component magnitude is same. Magnitude is same for orthogonal components with 90-degree phase shift. Here, magnitude is different for orthogonal components of 90-degree phase shift. So when it is said to be left-hand circular polarization means if the field rotates in clockwise direction, then it is said to be left-hand polarization. If field rotates in anti-clockwise direction, that is delta y minus delta x is minus of 2 power n plus 1 pi by 2. If it is plus pi by 2, then it is left hand circular polarization, that is field is rotating in clockwise direction. If it is minus pi by 2, then it is said to be rotating in anti-clockwise direction and the field is said to be right hand circular polarization, provided the two orthogonal components are having same magnitude. Now, as per the question, electric field component in x direction magnitude is 2, electric field component in y direction magnitude is 2. Now, the phase difference between delta phi is the phase difference between y component and phase difference between x component. So, it is pi by 2 minus 0, it is plus 90 degrees. Hence, it is said to be the field is rotating in clockwise direction, same magnitude, that is circular polarization, and field is rotating in clockwise direction. Hence, it is a left hand circularly polarized EM wave. The correct option is 2. Second option is correct. Next question. The maximal divergence equation for magnetic field is del dot B is equal to 0. Similarly, the Maxwell divergence equation for electric field is del dot D is equal to rho V, where rho V is the volume charge density. So here correct option is 2. Next question. The skin depth at 10 megahertz for a conductor is 1 centimeter. The phase velocity of electromagnetic wave in the conductor at 1000 megahertz or 1 gigahertz is about. So as we know, the skin depth delta is 1 by square root of pi of mu sigma, where phase velocity Vp is omega by beta. For a conductor, alpha is equal to beta, where alpha is attenuation constant is equal to phase constant. It is square root of omega mu by sigma or square root of pi of mu sigma, that is 1 by delta. So these are the formulas related to this question. Now they have given delta 1 is 1 centimeter and frequency f1 is 10 megahertz. So frequency f2 is 1000 megahertz and they ask to find skin depth at 1000 megahertz. So initially we need to find delta 2 to obtain the phase velocity. So now we will find the delta 2 at 1000 megahertz. So from this expression, so delta is inversely proportional to square root of frequency. So delta 1 by delta 2, skin depth at frequency 1 by skin depth at frequency 2 is square root of frequency 2 and frequency 1, the ratio of opposite frequencies. So delta 1 by delta 2 is its value is 1000 megahertz by 10 megahertz, square root of 100, so its value is 10. So delta 2 is, as we know, delta 1 is 1 centimeter, so delta 2 is 1 by 1 tenth of 1 centimeter, it is 10 power minus 3 meters. Now phase velocity, so phase velocity, now beta, phase constant beta is 1 by delta 2, so it is 1 by 0.1 centimeter, so it is 1000 radian per meter, 1000 radian per meter. Now phase velocity, so this is phase constant, phase constant at 1 gigahertz or 1000 megahertz. Now phase velocity Vp is equal to omega by phase constant at 1 gigahertz. Omega is 2 pi f, that is 2 pi, frequency is 1000 megahertz, 1000 mega 10 power 6, so that is 1 gigahertz, and beta is 1000. So on calculation its value is 6.28 into 10 power 6 meters per second, 6.28 into 10 power 6 meters per second. The correct option is 1. Next question. The time of variation of d by dt implied with reference to the field quantities in Maxwell equation is, it is a time harmonic field. The time harmonic field is a one which varies periodically or sinusoidally with time. So for the time harmonic field, dou by dou t is replicated with j omega. So electromagnetic wave is an example of time harmonic field. So correct option is 4. This time harmonic field is the one which varies periodically or sinusoidally with time. Next question. Given the equation del cross E is minus dou b bar by dou b bar by dou t is a generalization of, so it is a generalization of Faraday's law. So what the Faraday's law states that changing magnetic field induces electric field. Correct option is 4. Next, Gauss law is del dot D is equal to rho v. Biot-Savart's law is del cross H is equal to ideal cross AR by 4 pi r square, and Ampere's law is del cross H is equal to j bar plus dou d bar by dou t. So the correct option is Faraday's law. The Faraday's law is del cross E is minus dou b bar by dou t, where B is equal to mu H. So replacing B with mu H, we will get del cross E is minus of mu dou H by dou t by applying Stokes theorem. So this closed line integral of E bar dot dl bar is equal to open surface integral of dou b bar by dou t. Next question. The Laplacian of a scalar function v. The Laplace of scalar v is given as del square v, so that is del dot of del v. So divergence of, so this is divergence of gradient of scalar, divergence of gradient of scalar quantity. So the correct option is 1, divergence of gradient of v. Next question. The units of the term sigma by epsilon are, so we know sigma is conductivity, the units for conductivity is ohm meter inverse or mho per meter. The units of permittivity epsilon is farad per meter. The units of capacitance is farads. Farad per meter. The units of capacitance is farads and the unit for resistance is ohms. Now they have given sigma by epsilon. The time constant tau is equal to RC. The product of resistance and capacitance, it is nothing but a time constant. The units of tau are seconds. We know that epsilon by sigma is tau, so that is seconds. Now the units of sigma by epsilon are 1 by second. So for sigma by epsilon, the units are, it is 1 by tau, units is second inverse. So 1 by second, correct option is 2. Next question. The potential of electric dipole varies as 1 by r square. The electric field intensity varies as. We know that electric field intensity is potential per unit potential per distance r, as electric potential for a dipole V is inversely proportional to 1 by sorry directly proportional to 1 by r square, or inversely proportional to square of distance. So from this, electric field is proportional to 1 by r cube. So 1 by r cube. So in the question they have given, for a electric dipole, electric field intensity varies as r power minus 3. That is, electric field is directly proportional to 1 by r cube, or inversely proportional to r cube, or electric field is proportional to r power minus 3. So first option is a correct one. Question 59. Equipotential surface for a point charge R. So let us see some important points related to equipotential surfaces. So electric field equipotential surface is an any surface on which potential is constant throughout the surface. So potential is constant throughout the surface. It is called equipotential surface. So equipotential surface for point charge is equipotential surface for a point charge is concentric spheres. Similarly, equipotential surface for infinite line charge is coaxial cylinders having their axis at the line center. So this is a infinite line charge. So for this infinite line charge, equipotential surface is cylinders. So these are the coaxial cylinders. So all the cylinders axis coincides with the line charge. Next, equipotential surface for uniform electric field is, it is nothing but a planes. So planes normal to the axis. This is the equipotential surface for uniform electric field, and the electric field is perpendicular to equipotential surface. Next is, equipotential surfaces never intersect, and the direction of equipotential surface is from high potential to low potential. These are the points related to equipotential surface. So it is perpendicular to the electric field is perpendicular to the equipotential surface. Equipotential surfaces never intersect, and the direction of potential surface the direction of equipotential surface is from high potential to lower potential. So for the question, equipotential for the point charge is nothing but a spheres. So here it is shown, concentric spheres. Next, if the phase velocity of a plane wave in a perfect dielectric is 0.4 times of its value in free space, then relative permittivity of the medium is. We know that phase velocity Vp is 1 by square root of mu epsilon meters per second. So this in this case, mu can be replaced as mu or mu or mu naught, and epsilon can be replaced as epsilon naught epsilon r. So we know that 1 by square root of mu naught epsilon naught is 3 into 10 power 8. So it can be written as c, velocity of light. So that is 3 into 10 power 8 by square root of mu epsilon. So mu or epsilon r. So where Vp is a phase velocity. Given as per the problem, this phase velocity is 0.4 times of its value in free space. 0.4 times of 3 into 10 power 8. Now square root of mu or epsilon r. So for free space, mu r value is taken as 1. So here mu r is not mentioned, so its value is treated as 1. So mu r epsilon r is equal to 1 by 0.4. So from this, square root of epsilon r is 1 by 0.4 whole square, and epsilon r is 6.25. The units for relative permittivity of the medium is farad per meter. In the question, mu r is not mentioned, so its value is treated or assumed as 1. The correct option is 4, 6.25. Next question. A lossless line will be distortionless if the phase shift. So generally, for a distortionless line, the attenuation constant alpha is independent of frequency, and the phase constant beta linearly dependent on frequency. So attenuation constant alpha is independent of frequency, and phase constant, here it is phase shift. The phase constant is linearly dependent on frequency, so the correct option is 2. So some more points. The condition for distortionless transmission is R by L is equal to G by C. So this is a condition for distortionless transmission. It can also be written as Lg is equal to Rc. A line is said to be distortionless if output is output is an exact if output of this transmission line is exact replica of input, then the line is said to be distortionless line. And one more point is, every lossless line is distortionless but converse is not true. These are the points related to distortionless line. So one is the condition Lg is equal to Rc, and the line is said to be distortionless if output is an exact replica of the input, and every lossless line is distortionless but converse is not true. For distortionless line, attenuation constant alpha is independent of frequency, and phase constant or phase shift linearly depends on frequency. So the correct option is 2. Next question. For a transmission line with standing waves, the distance between voltage maximum and adjacent current minimum. So see here some important points related to maxima and minima, the distances between voltage maxima, current minima, like this. Two voltage minima are separated by lambda by 2 distance. Similarly, two voltage maxima are separated by lambda 2 distance. Two current minima and two current maxima are separated by lambda by 2 distance, that is I maximum minus I maximum. So the distance between one current maxima and other current maxima, the distance between one current minima and other current minima, the distance between one voltage maxima and other voltage maxima, the distance between one voltage minima and other voltage minimum is lambda by 2. Next, the distance between voltage maximum and current minimum, voltage maximum and current maximum, or voltage minimum, voltage maximum, current minimum and current maximum, the distance is lambda by 4. Next case, the voltage maximum and current minimum, the distance is same. So at the point where voltage is maximum, in that case the current is minimum. At the point where voltage is minimum, in that case the current is maximum, so the distance is 0. So from this, as per the question, the distance between voltage maxima and the adjacent current maximum, the correct option is 1 lambda by 4. Next question. To couple a coaxial line to parallel wire line, it is best to use so balloon. So it is best to use balloon to couple coaxial line to a two wire parallel line because it gives 1 is to 4, 4 is to 1 impedance, 4 is to 1 impedance transformation. So balloon gives 4 is to 1 impedance transformation. So the correct option is 4. Some key points. So quarter wave transformer, a transmission. So quarter wave means lambda by 4. So transmission line of lambda by 4 length is used to match load to a transmission line. And this quarter wave transformer and stub matching are the impedance matching techniques. There are two impedance matching techniques. One is quarter wave transformer and stub matching. Next question. The input impedance of short circuit lossless line of length less than quarter wavelength is. So input impedance of short circuit line, it is given as Zin is equal to ZSC, that is J Z naught tan beta L. So given length is lambda by 4. So we know that beta is 2 pi by lambda. Now this ZSC short circuit impedance, so given length lambda by 4, quarter wavelength. In the question they have given quarter wavelength, its length is lambda by 4. Now Zs is equal to J Z naught tan beta. Beta is 2 pi by lambda and length is lambda by 4. Now it is tan 90 degrees. J Z naught is characteristic impedance tan 90 degrees. So tan 90 is infinity. So it is open circuit. So the input impedance of short circuit line of length lambda by 4 is infinity. Therefore, input impedance of short circuit line of length lambda by 4 is infinity. So that is open circuit. Next, similarly, the input impedance of open circuit line of length lambda by 4 is 0, so that is short circuit. Therefore, a quarter wave line, that is a line of length lambda by 4, quarter wave line, or a line of length lambda by 4, a lossless transmission line. This line is assumed to be lossless transmission line. It transforms high impedance to low impedance and low impedance to high impedance. Hence, it is also called as impedance transformer. Impedance transformer. A quarter wave loss lambda by 4 lossless transmission line transform impedance from if input impedance is infinity, then output impedance for a lambda by 4 line will become 0. So that is open circuit to short circuit and short circuit to open circuit. Hence it acts as a impedance transformer. So few points related to this. If the length of lossless line is less than odd multiples of lambda by 4, then short circuit line behaves as a inductor and open circuit line behaves as a capacitor. So this is a lossless transmission line of length less than lambda by 4. If it is short circuited, it acts like inductive component. If it is open circuited, then it acts like a capacitor. Similarly, if the length of transmission line is equal to odd multiples of lambda by 4, then short circuit line behaves like a parallel resonant circuit and open circuit line behaves like a series resonant circuit. If length is lambda by 4, then this short circuit line behaves like a parallel resonant circuit, and length is lambda by 4 and open circuit line behaves like a series resonant circuit. Next, if the length of line is less than multiples of lambda by 2, then short circuit line behaves like a capacitor. If it is greater than lambda by 4 and less than lambda by 2, then short circuit line behaves like a capacitor and open circuit line behaves like a inductor. Next, if the impedance repeats for lambda by 2 distance and inverse for every lambda by 4 distance on a lossless transmission line. So impedance is repeating. For lambda by 2 distance, the impedance gets repeated and inverts. So inverts means 0 will become infinity and infinity will become 0. Short circuit will become open circuit and open circuit will become 0. For lambda by 4 distance, it is inverting, and for lambda by 2 distance, it gets repeated. So these are the points related to lambda for lossless transmission line of different lengths and their behavior. Okay. For 64 question, the correct answer is 3, purely inductive. So purely inductive. Next question. A transmission line of characteristic impedance 300 ohm is terminated by a load of 300 minus J 300 ohms. The transmission coefficient is, we know that the given characteristic impedance Z0 is 300 ohms and load impedance ZL 300 minus J 300 ohms. These are the given values of characteristic impedance Z0 and load impedance ZL. We know that reflection coefficient gamma is ZL minus Z0 by ZL plus Z0. So from this, calculate reflection coefficient gamma, that is ZL 300 minus J 300 ohm minus Z0, it is 300 by ZL plus Z0, 300 minus J 300 plus 300. So on calculation, its value is minus J by 2 minus J. Now transmission coefficient. So transmission coefficient gamma, tau, transmission coefficient tau is 1 plus gamma. 1 plus gamma. Transmission coefficient tau is 1 plus gamma. So gamma value is minus J by 2 minus J. So on calculation, its value is 2 minus 2J by 2 plus 2J. So it is 1.26 at an angle of minus 18.43. 1.26 at an angle of minus 18.43. The it is correct option is 1. The transmission coefficient is Option 1. Next, the characteristic impedance of a line is. So the characteristic impedance Z naught is a ratio of positively traveling voltage wave to positively traveling current wave at any point on the line. Now Z naught is given as V naught by I naught, so that is positively traveling wave, that is equal to R plus J omega L by gamma, where gamma is propagation constant. So it is given as square root of R plus J omega L by J omega L into G plus J omega C, or it can also be written as gamma by G plus J omega C, G plus J omega C. So it is written as R plus J omega L by G plus J omega C, where gamma is, it is combination of real constant and imaginary constant, where real parameter is attenuation constant plus phase constant, where R is a resistance per unit length of transmission line, ohm per meter, and G is a conductance per unit length of the transmission line, mho per meter. L is a inductance per unit length of the line, Henry per meter, and C is a capacitance per unit length of the line, Farad per meter. The correct option is 3. Z naught is equal to R plus J omega L by G plus J omega C. So on this, R plus J omega L into G plus J omega C is gamma, where gamma is a propagation constant. It is not Z naught. The transmission line has voltage standing wave ratio of 2, and then reflection coefficient is. So general reflection coefficient gamma is, or VSWR standing wave ratio is 1 plus gamma by 1 minus gamma. So in the question they have given standing wave ratio, it is 2, 1 plus gamma by 1 minus gamma. So on calculation it will result gamma value as 1 by 3. The correct option is 4. Next question. Input impedance of open circuit lossless line of length lambda by 5. So this length of the transmission line is given, length of the transmission line is lambda by 5. Length of the transmission line is equal to lambda by 5. So for this lambda by 5 is less than lambda by 4. So for length less than lambda by 4, for length less than lambda by 4, so it is open circuited lossless transmission line. So it is open circuited here, open circuited lossless transmission line. It behaves like a finite capacitive reactance. The transmission line is open circuited and input impedance is finite capacitive reactance. Correct option is 2. Next question. Which of the following condition will not guarantee a distortionless transmission line? So for distortionless line, characteristic impedance Z0, phase velocity Vp, attenuation constant alpha are independent of frequency, which can be realized as R by L is equal to G by C, or Lg is equal to Rc, and the transmission line is said to be lossless if the conductors of line are perfect. So the resistance is 0. That means the line is a perfect conductor and dielectric medium separating them is lossless. So if R is 0 and G is 0, the conductors of the line are perfect. It is a perfect conductor line, and the dielectric medium separating between them is lossless. That is G is 0. So this is one condition, and Lg is equal to Rc. This is one condition, and other condition for distortionless transmission is omega L far less than resistance and omega C far less than conductance. So these are the three different conditions for distortionless line. So which of the following does not guarantee? So it is option 3. So these three, option 1, option 2, option 4, these three conditions guarantee distortionless transmission. But option 3 doesn't guarantee distortionless transmission. Next question. When ZL, the impedance terminated to the load, it is ZL greater than Z naught, that is characteristic impedance. When ZL load impedance is greater than characteristic impedance Z naught, then VSWR on the line is, if suppose if the load is perfectly matched, so in that case load impedance ZL is equal to Z naught. So ZL is equal to Z naught, it is a matched load. In that case VSWR is 1. If it is short circuited load, so that is load impedance ZL is 0, VSWR is infinity. If it is open circuited load, so ZL is infinity, then VSWR value is infinity. If it is resistive load, so that is ZL is equal to RL, so some finite load resistance. If in this case there are two conditions, if this load resistance RL less than characteristic impedance Z naught, then VSWR is R naught by RL, characteristic impedance Z naught, and its real value is R naught. Next, in this condition, in case 4, if RL is greater than R naught, then VSWR is RL by R naught, where RL by R naught is normalized load impedance. The correct option is 3, normalized load impedance. Either it may be, so ZL greater than Z naught, RL greater than R naught, then load impedance, then VSWR is on the line is RL by R naught. This RL by R naught is also called as normalized load impedance. So correct option is 3. Next question. Hartley circuit, Hartley oscillator circuit uses. In Hartley oscillator, there are two inductors. These two inductors are in series and one capacitor. In Colpitt's oscillator, there are two capacitors in series and one inductor. So inductor is L. Similarly, in Colpitt's oscillator, there are three capacitances and one inductor. In reactive reactance network, it is similar. This clap oscillator is similar to Hartley oscillator with additional capacitor in series with the inductor. In Hartley oscillator, two inductors in series and one capacitance in the reactive network. In Colpitt's oscillator, two capacitance in series and one inductor in the reactive network. In clap oscillator, three capacitance and one inductor in the reactive network. It is similar to Hartley oscillator with additional capacitor in series with the inductor. This Hartley oscillator uses tapped inductor for feedback in the tank circuit, and Colpitt oscillator uses tapped capacitor. Here it uses tapped inductor, tapped inductor for feedback in tank circuit, for feedback in tank circuit. In Colpitt's oscillator, it uses tapped capacitor for feedback in the tank circuit. Let us see the diagrams for this. So it is, first one is Hartley oscillator. So this portion is tapped inductor circuit, tapped inductor circuit, and L equivalent impedance is L1 plus L2 plus 2 times of mutual inductance. If those two inductors are in series aiding connection, then resonant frequency or oscillation frequency is 1 by 2 pi square root of L equivalent into C. Similarly, this circuit diagram shows Colpitt's oscillator. This is Colpitt's oscillator. In feedback circuit, there are tapped capacitor. Two capacitors are connected in series with one inductor. So correct option is, in Hartley oscillator circuit uses a tapped inductor. Correct option is 2. Next question. Relaxation oscillator is 1. So this relaxation oscillator and UJT oscillator produces, these are non-linear oscillators. These relaxation and UJT oscillators are non-linear oscillators, and produces non-sinusoidal output, and produces non-sinusoidal outputs. Relaxation oscillator or a stable multivibrator or a square wave generator has no stable states, has no stable states. It has stable states. Option 1 is wrong. Oscillate continuously? No, it produces non-sinusoidal output. Option 2 is a correct one. So relaxation oscillator or a stable multivibrator or a square wave generator has no stable state and storage element causes abrupt change in the output waveform. Relaxation oscillator produces non-sinusoidal output. Relaxation and UJT oscillators are non-linear oscillators. Non-linear oscillators or function generator generates square wave, triangular wave or pulses, etc. They use multivibrators as a functional blocks. Correct option is 2. Next question. The circuit shown in the figure is in. So it is a positive clamper circuit. Option 3 is a correct one. So clamper is a nonlinear circuit because a diode element is present, hence it is a nonlinear circuit that shifts the waveform to a desired level without changing the peak to peak RMS value of the signal. Peak to peak value, there is no change in magnitude of the signal, peak to peak value or RMS value of the signal, and there is no change in the shape of the signal. Shape of signal. So clamper is a nonlinear circuit that shifts the waveform to a desired level without changing the peak to peak value or RMS value or without changing the shape of signal. So this clamper circuit is used to restore or reinsert DC component into the waveform that has been lost during processing. Hence clamper circuit is also called DC restorer or DC reinserter. DC reinserter. So let us see the diagrams for positive clampers and negative clamper. So negative clamper which adds negative DC voltage, which is also called positive peak clamper. Positive clamper which adds positive DC voltage, also called negative peak clamper. So from this circuit, so this is a positive clamper. So positive clamper without bias. Ideal positive clamper. Next question. The required condition to get sustained oscillation is, so the condition for oscillation from Bark-Hassan criterion is, first one, the magnitude of loop gain must be at least equal to 1. So magnitude of loop gain A beta must be at least equal to 1 so that oscillations are sustained. And the second condition is total phase shift around the loop must be equal to 0 degrees or 360 degrees. The total phase shift around the loop, so that is angle A beta, angle of A beta, so it is around 360 degrees or 0 degrees. The correct option is 4. Both 1 and 2, A beta is equal to 1 on Bark-Hassan criteria. So the correct option is, the required condition is option 3 as well as option 2. So it is option 3 as well as option 2. The correct option is fourth option. Both 3 and 2 are correct. Next question. In a common emitter amplifier, the unbypassed emitter resistor provides. In common emitter amplifier has unbypassed. If common emitter amplifier has unbypassed emitter resistor, then output signal is output signal, sampled is current signal, and feedback signal is voltage signal. So that means current sampling, voltage mixing. So it is output signal sampled is current. So that means current sampling, voltage mixing. Current sampling at the output and voltage mixing at the input. So it is nothing but a current series feedback, current series feedback. So example is transconductance amplifier, also called transconductance amplifier. In a common emitter amplifier, the unbypassed emitter resistor provides current series feedback. So current series feedback. Correct option is 4. Next question. Which type of gate is shown in the figure? So from this gate 1, let us assume this is gate 1, gate 2, gate 3, gate 4 and 5. So we need to calculate the final output at the output of gate 5. So gate 1 is not gate. The output of gate 1 is, for input A is A bar. So gate 2 is not gate. A NAND gate with two inputs tied, it will behave like a not gate. So the output is A bar. So let us assume X is the output of gate 3 and Y is the output of gate 4. So now X is NAND of A bar comma B. So now X value is A plus B bar. So similarly Y is NAND of NAND gate of B bar comma A. So it results A bar plus B. Now final output is XY given to NAND gate. So let us assume this is Z. So Z is equal to NAND of X comma Y. So the output here is A bar B plus AB bar. So it is XOR gate. So it results XOR gate, that is A XOR B, A XOR B. So correct option is 1. Next question. Full adder can be implemented by to implement a full adder, it requires two half gates, two half adders and one OR gate. To implement a full adder, the total number of multiplexers required is 7. 7 multiplexers are required to implement a full adder. To implement full adder using two input NAND gates, it requires 9 NAND gates. The number of two input NOR gates required to implement full adder is 9. So using only half adders, it is not possible to implement full adder. Using AND gate and OR gates, it is not possible to implement full adder. Using decoders, it is not possible to implement a full adder. But using multiplexers, we can implement the full adder. The correct option is 2, because multiplexer is a universal logic circuit. Hence, it can be used to implement a full adder. Multiplexer is universal logic circuit, and the number of multiplexers required to implement full adder is 7. Number of multiplexers required to implement half adder is 3. So 7 multiplexers are required to implement full adder and 3 multiplexers are required to implement the half adder. So correct option is 2. Next question. The dual of A plus B plus AC plus D is, we know that the dual expression is equivalent to writing a negative logic for the given Boolean function. So the conversion of, so duality theorem means simply the conversion of negative logic to positive logic and positive logic to negative logic. In this duality theorem, replace OR gate with AND gate and replace AND gate with OR gate. The complement any 0 or 1 appearing in the expression and keep literal as it is. So variable is not changed. Only 1 means it will be replaced with 0 and 0 means it will be replaced with 1. Every Boolean function there is a corresponding dual function. The dual expression can be used to convert negative logic to positive logic and positive logic to negative logic. Next, the duality theorem, the dual of Boolean function can be found by switching the logical AND gate or logical OR operators and switching zeros and ones. So 0 is switched to 1 and 1 is switched to 0. AND gate is switched to OR gate and OR gate is switched to AND gate. So this is a theory related to duality theorem. So for the given expression A plus B plus AC into D, so the duality can be written as, here R operator is replaced with AND operator, A and B and A plus C dot D. So the correct option is 4. So fourth option is a correct one. Next question. NAND gate with positive logic will operate as, NAND gate with positive logic is equivalent to OR gate with negative logic input is equivalent to OR gate with negative logic inputs. So correct option is 4. NAND gate with positive logic is equivalent to OR gate with negative logic input. So that is bubbled OR gate is equivalent to NAND gate Bubbled NAND gate is equivalent to OR gate. Bubbled NOR gate is same as AND gate. AND operation. Bubbled AND gate is same as or equivalent to NOR gate. Next question. The main advantages of CMOS complementary metal oxide semiconductor CMOS logic over TTL circuit, transistor logic circuit is. So let us see the advantages and disadvantages of CMOS over TTL. So advantage of CMOS is power dissipation per gate is very less. CMOS has very less power dissipation, and then high noise margin. CMOS have very high noise margin and high fan out. It can able to drive more number of similar gates, and low speed power product, and the circuit complexity is also moderate. These are the moderate circuit complexity. These are the advantages of CMOS. But the disadvantage of CMOS is decreased speed of operation. So decreased speed of operation. So the main advantages of CMOS over TTL is much reduced power dissipation. The correct option is 3. Correct option is 3. Next question. So let us see the parameter and TTL the parameter comparison of TTL and CMOS. In CMOS, the power dissipation is, in TTL it is 10, in CMOS it is 0.01. Very less power dissipation in CMOS. Next question. The radiation pattern of antenna used in VHF omnidirectional range is. So generally, VHF omnidirectional radio range, that is VOR. VHF, very high frequency omnidirectional radio range, VOR, is a type of short range radio navigation used for finding the direction of incoming aircrafts, which uses VHF band from, this is the frequency of VHF band from 108 megahertz to 11 117.95 megahertz. So in this VHF band, turnstile antennas is used. It is widely used. Turnstile antenna is widely used for VHF omnidirectional communication, and turnstile antenna arrays radiates equally in all directions, producing omnidirectional radiation in horizontal plane. So omnidirectional radiation in horizontal plane. As per the question, the radiation pattern of antenna used in VHF omnidirectional range is, the radiation pattern is omnidirectional. Next, some more points. The turnstile antenna is frequency fed for local area transmission at VHF or UHF range. Turnstile antenna has set of two dipole antennas aligned at right angles to each other, fed with 90 degrees out of phase input signals. When mounted horizontally, this turnstile antenna has omnidirectional radiation pattern in horizontal plane. When turnstile antenna is mounted vertically, then its directional pattern at a right angle to its plane and is circularly polarized. These are the points related to turnstile antenna which is operating at VHF plane, VHF band. Next question. A half wave dipole operates at 30 megahertz. Given frequency of operation is 30 megahertz and direct to gain of 1.5. So for dipole of length lambda by 2 or half wave dipole, the maximum direct to gain or directivity is 1.5. We know the relation between directivity and effective aperture area. Directivity D is 4 pi AE by lambda square. 4 pi AE by lambda square. So from this frequency of operation given is 30 megahertz. Lambda is 3 into 10 power 8 by 30 into 10 power 6. Therefore wavelength is 10. Lambda square. Now directivity is, substitute these values in lambda values in directivity expression, that is 1.5 is equal to 4 pi effective aperture area. Lambda is 10 meters, so that is lambda square is 100. So from this, in the question they have given efficiency is 100%. So efficiency is 100, that is 1, efficiency is 100%. Therefore effective aperture area is 150 by 4 pi. Its value is, so 150 by effective aperture area is 150 by 4 pi meter square. For antenna effective aperture area is, next, 150 by 4 pi. Next, in the question they have given the plane wave carrying pi watt power per square meter is incident on the antenna. So incoming power is, so power input or incoming power pi is pi watt per meter square. Now the total power P out is input power into effective aperture area. So that is pi watt per meter square into 150 by 4 pi meter square. So it's value is 36, that is 150 by 4, 36.5 watt. The power received is 36.5 watt. Next question. Aggie-Wood antenna. So Aggie-Wood antenna consists of driven element. So consists of driven element, one or more directors. Sorry, one or more directors and one reflector. So Aggie antenna consists of driven element. So the driven element is dipole or folded dipole along with a reflector and one or more directors. That is, it is an array consisting of driven element, one or more parasitic elements. Basically, three elements, that is driven element, reflectors and director. So these director and reflector are parasitic elements, and driven element which is a dipole or folded dipole. So the length of director is 5% less than the driven element, and length of reflector is 5% more than the driven element. So these are the general scenarios. Let us see the diagram of Aggie-Wood antenna. So this is a reflector whose length is higher when compared to all the directors, and these are the director 1 and director 2. So in practice, reflector length is 500 by f mega frequency in megahertz feet, and this is the director length, and this is a director length, driven element length, and reflector length. Next, as per the question, Aggie antenna consists of. So Aggie antenna consists of dipole, reflector, and one director. The length of director is 5% less than the driven element, and length of reflector is 5% more than the driven element. Directors carry inductive currents. So this director carry inductive currents, and reflectors carry capacitive currents as their lengths are smaller and larger than the resonant length respectively. The parasitic element of driven element, the parasitic element in front of the driven element is director. So this is parasitic element in front of the driven element. This is driven element. The parasitic elements in front of the driven element is director, and the parasitic element backside of the driven element is reflector. Next question. Higher bandwidth implies. So generally the gain bandwidth product is constant. Gain into bandwidth product is constant. If gain increases, bandwidth or beam width decreases. If gain decreases, beam width is increased. So gain bandwidth, or we can tell gain beam width product. So let us see here. So this is an isotropic antenna. For isotropic antenna, gain is unity. It radiates in all directions. All It radiates signal in all directions. Omnidirectional radiation pattern. This isotropic antenna radiates signal in all directions, and gain is unity. So but there is, the green line indicates this is a directional radiation pattern. The radiation pattern is directional, but here beam width is less but gain is more uh, when compared to isotropic antenna. This green line radiation pattern has more gain. So higher the bandwidth implies lower directivity. For 84 question, option 1 is correct. Lower directivity or lower gain. Next question. The standard reference antenna for direct to gain is. So the standard reference, this isotropic radiator is a standard reference antenna for direct to gain measurements. So some more points related to isotropic radiator is, this isotropic radiator is a fixous radiator which radiates energy uniformly in all directions. Hence it is also called unipole, because it is radiating energy uniformly in all directions. So it is radiating energy uniformly in all directions. This is a blue curve. Next, it is also called, this isotropic radiator is also called as lossless hypothetical antenna, or a theoretical antenna, or an imaginary antenna with which All practical radiators are compared. Hence, isotopic antenna is used as a standard reference antenna for gain measurements of other antennas. Practically, this isotopic radiator doesn't exist whose gain is unity or 0 dB. The gain of this isotopic antenna is unity or 0 dB, and this isotopic antenna is a non-directional antenna. Next question: which of the following is very useful as multi-band high frequency receiving antenna? So frequency independent antennas are log periodic antenna, half wave dipole, that is lambda by 2 antenna, and conical horn antenna, helical antenna, are frequency independent antennas. Then log periodic antenna or log periodic array is a multi-element directional antenna. Is an multi-element directional antenna designed to operate over a wide range of frequencies, or designed to operate over wide band of wide range of or wide band of frequencies. So correct option is 4, log periodic array. Very useful multi-band high frequency receiving antenna. Next, log periodic antenna is very useful as multi-band high frequency receiving antenna. Multi-band high frequency receiving antenna. Next question: indicate the antenna which is not a wideband. So Marconi antenna is not a wideband antenna, but discone antenna, folded dipole, log periodic, helical antenna all are wideband antennas. So correct option is 1. Next question: a quarter wave monopole. Given quarter wave monopole means length of antenna is lambda by 4 and operating frequency is 1 megahertz. 1 megahertz have an overall length of, so lambda is c by f. So we know that length of quarter wave monopole is lambda by 4 and we need to calculate the length for the frequency of 1 megahertz. So lambda is equal to c by f, that is 3 into 10 power 8 by 10 power 6. So 300 meters is wavelength and length of the monopole antenna is 300 by 4, that is 75 meters. So correct option is 2. Next question: the radiation resistance of half wave dipole. So first to see the definition of radiation resistance. Radiation resistance is fictitious resistance, is a fictitious resistance when substituted in series with the antenna will consume same power as it is actually radiated. It can also be said as radiation resistance is fictitious resistance whose power consumption is equivalent to the power radiated. Or radi- radiation resistance gives a relation between total energy radiated from the transmitting antenna and current flowing through the antenna. These are the various definitions related to radiation resistance. Next is the radiation resistance of half wave dipole is 73 ohms and radiation resistance of quarter wave monopole is 36.5 ohms. The radiation resistance of folded dipole is 292 ohms and radiation resistance of Hertzian dipole is 80 pi square L by lambda whole square. These are the radiation resistance of different antennas. For half wave dipole 73 ohms, quarter wave monopole 36.5 ohms, folded dipole 292 ohms, and for Hertzian dipole, so for folded dipole means 4 times of half wave dipole, 4 into 73, that is 292, and for Hertzian dipole it is 80 pi square L by lambda whole square ohms. So radiation resistance is, it is a fixed resistance when substituted in series with the antenna will consume same power as it is actually radiated, or it is a fixed resistance whose power consumption is equivalent to power radiated. The correct option is 3, 73 ohms. Next question. The unit of magnetic field of electromagnetic radiation at any place is usually expressed in. So units of, so magnetic field intensity H, magnetic field intensity H, ampere per meter. Electric field intensity E, units is volt per meter. And electric flux density D is coulomb per meter square, coulomb per meter square. And magnetic flux density B is Weber per meter square or Tesla. As per the question, radiation magnetic units of magnetic field of electromagnetic radiation. So magnetic field H is ampere per meter, so correct option is 1. Next question. When an electromagnetic wave meets perfect conductor, electromagnetic wave is totally reflected. So this is incident component and this is reflected component, and transmitted component is 0. So when an electromagnetic wave is totally reflected, the electromagnetic wave is totally reflected when it strikes a perfect conducting surface. So no transmitted wave component. So for a perfect dielectric medium, it behaves like a perfect transmitter of EM waves. So in this case, reflected component is 0, the complete wave is transmitted. For perfect dielectric, so electromagnetic wave incident on a perfect dielectric medium is totally transmitted and there is no reflected component here, but entire signal is reflected if it is a perfect conductor, and transmitted component is 0. So correct option is 2, completely reflected when it meets a perfect conductor. The absorption of radio waves by the atmosphere depends on, the absorption of radio waves in the normal atmosphere depends on frequency, depends on their frequency, and it is relatively insignificant. The absorption is relatively insignificant at frequencies below 10 gigahertz. So correct option is 3. The absorption of radio waves by atmosphere depends on their frequency. Next, wave attenuation due to absorption does not depend on the distance from the radiating source, but rather depends on total distance that a wave propagates through the atmosphere. One is frequency and does not depend on the distance, but rather depends on the total distance that the wave propagates through the atmosphere. Next question. The frequencies in UHF range propagates by means of. So generally there are different types of wave propagation. For ground wave propagation or surface wave propagation, it can be used up to 2 megahertz. The frequency of signal is up to 2 megahertz. For skywave propagation, up to 2 megahertz. For skywave propagation or ionospheric propagation, the frequency of operation is 2 to 30 megahertz. And for space wave propagation or tropospheric propagation or line of sight propagation, so it is greater than 30 megahertz. The frequency of operation is greater than 30 megahertz. For tropospheric scatter, it is greater than 300 megahertz. Tropospheric scatter, it is greater than 300 megahertz. Ductal propagation or super refraction occurs mainly at UHF and microwave frequencies. The frequencies in UHF range are normally propagated by means of space waves. So by means of space waves, correct option is 4. So let us see the frequency, UHF frequency range is 300 megahertz to 3 gigahertz. So in this range, the propagation is through space waves. Next question. Maximum usable frequency FMUF and critical frequency FC. The relation between this maximum usable frequency and critical frequency is maximum usable frequency. It is given by secant law, SECANT. So the relation between these two, maximum usable frequency and critical frequency, is given by secant law. It is given by secant law, where maximum usable frequency is secant phi of critical frequency FC. So secant phi, where phi is the angle of incidence. Phi is angle of incidence. So in this, for secant 0 it is 1. So as angle of incident increases, secant value increases. So generally this maximum usable frequency is greater than or equal to critical frequency. If the angle of incidence is 0 degrees, then maximum usual frequency and critical frequency are same. So in rest all the cases, if angle of inclination is greater than 0, then all the cases maximum usable frequency is greater than critical frequency. So maximum usual frequency is higher than critical frequency. Next question. The absorption of radio waves in the atmosphere depends on frequency. The question is repeated. In this question paper, two questions are repeated. In 2013 APPSC Government Polytechnic Lecture Examination, two questions are repeated. Next, ductive propagation occur only when transmitting antenna height is. The correct option is 1. So ductive propagation occur only when the height of antenna is less than the height of the duct. So you just see this image here. This blue line indicates. So this blue line indicates height of the duct and green line indicates height of the transmitting antenna. So duct height of the transmitting antenna. So in this case, the height of the transmitting antenna is much smaller when compared to the duct height. So this red color indicates trapped electromagnetic wave inside propagating inside the duct. So this diagram shows. So this is duct height and this green line is transmitting antenna height. So duct height is much higher than transmitting antenna height, then only duct propagation will occur. So for 96th question, correct option is 1. So duct propagation can occur only when the height of transmitting antenna is less than the height of the duct, or height of duct is greater than the height of transmitting antenna. So let us see some more points. So this duct propagation, also called super refraction, is due to temperature inversion. Duct means the region of cool air present between the layers of warm air. So ductive propagation occurs only when height of the transmitting antenna is less than height of duct. So this is a condition. Option 1 is correct. Next, duct this duct behave as a wave guide in atmosphere and guides the high frequency radio waves to the other end along the curvature of earth by successive refraction. Hence it is also called super refraction. Next question. The frequencies in UHF range propagates by means of, this question is also repeated, by means of space waves. Next question. The dominant mode in rectangular waveguide is. So dominant mode means modes having lowest cutoff frequency or the modes having highest cutoff wavelength is dominant mode, and this dominant mode in a waveguide is a lowest attenuation mode. For a rectangular waveguide, the dominant mode is TE10 mode. TE10 mode if A greater than B. A, B are the dimensions of waveguide, and it is TE01 mode if A less than B. So here dimensions are not mentioned and this is taken as generalized case. So the dominant mode is TE10 mode. Correct option is 2. Similarly, few more points. TE11 is a dominant mode in cylindrical waveguide. For a cylindrical waveguide, TE11 is a dominant mode for cylindrical waveguide. TM110 is a dominant mode in circular cavity resonator of A greater than D. TE111 is a dominant mode for circular cavity resonator if D greater than 2A. And TE101 is a dominant mode of rectangular cavity resonators. So in the question they have given rectangular waveguide, not a cavity resonator or cylindrical waveguides, only rectangular waveguides. If it is cylindrical waveguide, dominant mode is TE11. If it is cavity resonators, and these are the corresponding dominant modes. The advantage of dominant mode is lowest cutoff frequency and higher cutoff wavelength with low attenuation in that mode. If signal is propagated in the dominant mode, the attenuation for that signal is much lower. Next question. The position of the probe for half power points in the slotted line of microwave bench are interpreted to measure. Correct option is 4. High voltage standing wave ratio. So for low VSWR measurements, for VSWR less than 10, we will go for the direct measurements. If VSWR is greater than 10, for measurement of high voltage standing wave ratio, we will use double maxima method. So in this double maxima method, D1, D2 are the points where power is twice that of minimum power, or voltage is root 2 times that of minimum voltage. So VSWR is lambda g, where lambda g is a guided wavelength, lambda naught is free space wavelength, and this relation between lambda g and lambda naught is lambda g is equal to lambda naught by square root of 1 minus lambda naught by lambda c whole square. So where lambda naught is free space wavelength and lambda c is the cutoff wavelength of the waveguide. So the position of the probe at half power points, power is half of the minimum power at twice that of minimum power in a slotted line of microwave branch as interpreted to measure higher VSWR, high voltage standing wave ratio, that is for VSWR greater than 10. Next question. So a microwave junction is supposed to be matched at all ports if S matrix is. So if all the diagonal elements of S matrix are equal to 0, then microwave junction is said to be perfectly matched. So that is reflection. Signal reflection is 0. Signal reflection at ports is 0. If all the diagonal elements of S matrix are equal to 0, then microwave junction is said to be perfectly matched at all ports. Therefore, the signal reflection at the ports is 0. Entire signal is transmitted. So, correct option is all the diagonal elements are 0. Correct option is 2.